Today I'm going to talk about functional programming. By the way, I'm Mark Bastian for those that don't know me. Today I'm going to talk about functional programming, and I'm calling this functional programming from the fire hose because I'm going to be talking about a lot of content today. As I was thinking about this talk, I had a big challenge. If I talk about the traditional aspects of functional programming, what it's all about, the theory, monads, category theory, I'm going to lose everybody, and you're all going to be bored. You're not going to get anything out of it, and you're going to go back to programming in your object-oriented programming Java ways. So instead, I could spend 30 minutes showing you examples, and I could show you 30 minutes worth of Clojure in the Scala, and that would be unrecognizable, and you would scream and say, I'm not going to do that. That's unfamiliar. So instead, I'm going to do both. So I'm going to try to spend just a couple of minutes talking about what is functional programming, and then I'm going to spend the rest of the time showing some examples. So what is functional programming? In computer science, functional programming is a paradigm like object-oriented programming, but instead of thinking of the world in terms of objects, these are the tangible objects, we think of the world in terms of assembling mathematical functions that have immutable state. So let's talk a little bit more about that. There are really three fundamental tenets of functional programming. The first is that you need functions, and I mean true functions, mathematical functions, and I will talk about that. You need immutable data, that is values, and finally your functions need to be free of side effects. So let's have a slide on each of those. Functions in functional programming languages are types, just like ints, doubles, and strings are types, and just like objects in object-oriented programs are types, which means I can assign functions to values, I can pass functions around, I can pass them into functions, I can return them from functions. This is different from object-oriented programming in which all methods are assigned to an object, therefore I have to pass the object around. I can't actually pass the function itself or the method around. Functional programming functions are mathematical functions, and you get all the special properties, if you remember back to your Calculus 101 course, that you get with mathematical functions. I get consistent results. This is something I cannot emphasize enough. With the true function, I pass some value in, let's say it's x plus 1. I pass 2 in, I always get 3 out, no matter what. I pass 4 in, I always get 5 out. I will never pass 4 in and get 6 out. So that seems very simple and trivial, but that is critical to the effectiveness of functional programming. I get all of the mathematical attributes that I get with true mathematical functions if I'm doing functional programming. I can compose my functions together to get more complicated functions. I can substitute the result of a function into a function's place for optimization. I can partially evaluate a function to get a newer function. Okay, tenet number 2 is values. Values, when we talk about functional programming, means immutable data. So in every language out there, when you think about doubles and ints and generally strings, you think of them as values. They don't change. 5 does not change. Pi does not change. Some things do change. If you're to think of something that is a value versus not a value, my date of birth is a value. It does not change. My age does change over time. It is not a value. In functional languages, in addition to primitives, we have value types and immutable collections, which means not only are my primitives immutable, but my classes are immutable. Once I create them with initial fields, those fields are locked down, and I have good methods for equality and hash code, and the same thing applies for collections. Collections, once I build them, do not change ever. This gives you some awesome powers. One, values are implicitly concurrent. So in a multi-core world, that's great. Values do not require deep copying. If I have most of my data that's shared, if I want to make a one-off version of that, I can keep most of my old value, and so I really don't have to incur a lot of memory overhead for that. Values are required, so this is a necessary but not sufficient condition for true functional programming. Values are required for functional consistency. If I have something that I pass into a function and do a computation on, and that value that I passed in changes midstream, I have an indeterminate result, and so I've lost my power of FP. Values are easy to reason about. They never change in time, so I can think about what they are no matter how complicated they are, and so that's pretty nice. In true FP, it's values all the way down. Third tenet of functional programming is that there are no side effects in functional programming. Anything that affects your function outside of what goes in and the actual algorithm itself is a side effect, meaning if I have to read in a configuration file before I pass my values in to get a result, that is a side effect. Mathematical functions implicitly do not have side effects, so this is a rule that we have to impose when we're talking about computer programming. Examples of side effect include reading and writing from a disk, printing to a screen, keyboard I/O, and you think about that and you think, well, if I can't do any of that, how can I have a useful program? Well, the answer is, in practice, there will be side effects. However, in functional programming, you minimize and you contain your side effects. Okay, in summary, FP treats computation as the evaluation of mathematical functions, and you need these three things. You need real functions, you need values, and you do not want side effects. So let's jump into our examples. Okay, just so you know, I'm going to go fast. My goal here is not to teach functional programming and 3 different programming languages in 30 minutes, so I will hit the high points, but for completeness, I've included all the source code in all the slides, so when you look at the slides, you can scroll down and see everything I'm doing. Okay, our first example is collection abstraction. This is a very common example when you kind of get introduced to functions and what they're all about. If you are used to object-oriented programming, there are things that you do all the time that are repetitive patterns that you may not be aware of or you may not think about. For example, if I have a collection of integers, I may iterate over that collection and pass the square of all those integers into a new collection. That's called mapping. I map one type to another type. I may filter certain elements out. Maybe I only want to keep the evens or the odds in my new collection. Again, that's a pattern called filtering. I may want to reduce all of my elements to a single value, such as their sum. Again, it's a pattern. I want to find a certain element in a function, the largest or the smallest value. Again, it's a pattern. I want to check for the existence of an element that satisfies a predicate. Maybe do I have any even numbers in my collection? If so, return it. Again, it's a pattern. These patterns, when you're doing standard object-oriented programming, generally incur a large amount of boilerplate in terms of their overhead. So I want to look at how functional programming can help and how we can abstract these details away. So first, let's look at an example using standard Java. So if I'm pre-Java 8, before lambdas, this is what I would do if I wanted to map a collection to its square. So I have this method, map. It takes a collection of integers in. It initializes an output container called output, and then I iterate over all of my inputs, and I add the output of my my function, my I squared, into the output collection and return that. So I am mapping my initial set of integers to their squares. Here's another example. If you look at this, I'm doing exactly the same thing, only if you look at the output.add, rather than returning the squares, I'm returning the doubles of my collection. So it's a pretty basic example. I think everyone can see what I'm doing here. But what you'll see is everything is identical except for one single operation. The only difference is one had I times I, the other one had 2 times I. So can I abstract all this code away and have some nice little clean interface in which I just pass in just a function and just that little thing that I want to do using object-oriented programming? Kind of, but not really in object-oriented programming land because functions are attached to objects. But if you don't believe me, let's see how you do it. Okay, here is the object-oriented API for how I would hide all that. First of all, I have an interface called I operation that has a single function that takes thing. We're using generics here because it's not always mapping i's to I or doubles, integers to integers. It could be integers to doubles or foos to bars, whatever it is. So I take something in, I return something out. I have a map function that takes my collection in. It now also takes this this class in. It constructs my returning container, it iterates over it, it adds things based on that operation that I've defined, and then it returns the output. So it's ugly, but I can do it, sort of. So here's how I would use this in practice. So here I've got a main function. I add 1,000,000 integers to my collection. I now call my map function, and I pass my integer collection into it, and now I have this anonymous inner class in which I invoke an I operation, or I create one, and I override my apply method, and I turn my integer into its square root, so I'm mapping ints to their roots. You look at this, and it isn't particularly satisfying. I got rid of my my loop and my container that receives everything, but now I've added this large amount of boilerplate to add one single function, the square root. So kind of ugly. So what would we do if we had functions? Well, in Java 8 you have functions. They're not quite as good as other language functions, but they're better than nothing. They're called lambdas. And so you have the same collection of ints, and you call this stream method that streams every element of my int. I map it, and again, I've been talking about mapping elements to elements. And in here I have this I arrow II, that is a lambda, which is an anonymous function that takes the element I and it maps it to its square. I collect it and I pass it to a list. So if I compare that to my previous solution, I've gone, if I ignore the line break, from 6 lines of code down to 1. So, and I think it's pretty readable. You can read it from left to right, kind of like you read a sentence almost. So that's pretty cool. It's hidden away all the details. In other languages, you can do the same thing. So here's a Java 8 version, a Scala version, and a Clojure version. One thing to point out is if you ignore the line break, the Scala and Clojure versions are probably about half the length of the Java version. Also, something to point out is in my previous example, I ignored the fact that I had to pre-initialize my integer collection in Java. In Scala and Clojure, functionality is provided to just inline create my range of values from 0 to 1,000,000. So they're even smaller because the ability to construct data, manipulate data, that's really what FP is all about. Okay, so in conclusion, for first-class functions, they allow you to abstract away repetitive behaviors. And you have to think about this when you're programming. What's more common, domain objects or patterns of action? Domain objects generally, unless they're very general domain objects like date or time or something like that, really are not things you're going to use in every program. But patterns of action you use everywhere. You use collections everywhere. So if you program for patterns using first-class functions, you get a lot of reuse. It reduces the amount of code you have to write. It also reduces your potential for errors. If I have a correct solution once, that solution works correctly everywhere I use it. If it turns out that there's a bug, I only have to fix that bug in one place and everybody else gets the fix. Okay, so example 2 is values. Remember I talked about how values are immutable data and they're an important part of functional programming. Values are concurrent, they're easy to reason about. You lose your FP predictability guarantees if you do not use values. So for true FP, again, it's values all the way down. Everything from your most complicated data structure down to your primitives are values. Okay, so here's a Java example, concurrent modification. What happens in this example? I'm using lambdas because I know about lambdas. I have my integer collection. What I want to do, if you jump down below that thread, is I want to filter out the odd, so I only have a collection of even numbers from 1 to, or 0 to 1,000,000. But right before I do that, I invoke this thread that constantly removes the first element of my collection. So what's going to happen here? This. So even though I have lambdas, I have not solved all the world's problems. So what happened? Well, it's pretty obvious. 2 threads were concurrently operating on a single mutable data structure. I can't tell you exactly where things broke or what broke, but if you think about it, the results should be indeterminate. I don't know what's going on there. I know I've got 2 things that are mutating and 2 things that are mutating it at once. Here's how I would do it in a different language. I cannot do this in Java because Java does not have immutable data structure, so it's time to move to a better programming language. So this is Clojure. Clojure, I'll walk you through a few of these things. I don't want you to learn Clojure in one day, but first we define int_vec, so that's a value, to be a range of 1,000,000 elements that I put into that square bracket, which is a vector. So I'm creating a list for a vector of 1,000,000 elements. This feature does the same thing as that thread. It iterates, and at every iteration in my loop, I pop off the first element and I return the rest of my collection to the loop recursively. And then finally, down below that, that area that starts with count, what I do is I take my int_vec, I filter out the odd values, so I only keep the evens, and I count them. And you can see below the result. The result is I print all done, that's the result of my feature, and the count is 500,000. It's exactly half of my initial range. Well, why did it work? Because int_vec is immutable. It is a value. It never changed after I initialized it. The feature didn't actually modify int_vec. What the feature did is it just operated on views into int_vec. So it started with int_vec, and then it looked at the rest of int_vec minus the very first element, and then the rest of that minus the next element, all the way down until it was done. The filter and count operation below that only operated on the initial int_vec. So effectively, that feature was a null op. It didn't do anything. So it's kind of cool. So in conclusion, values are powerful concepts. It is a key requirement for FP. You get implicit concurrency, you can reason about them, they're easy to manipulate, they're easy to analyze. In terms of languages, if you're like, hey, now I want to go do this, what language should I choose? So the two FPs, I'm assuming most people here are Java programmers, that's why I'm not talking about Haskell or Lisp, but if you are looking at Scala, it has good value support. It has both immutable and mutable collections, and by default you should be using immutable collections. It has case classes. Case classes produce Java classes, which have finalized fields and also implement hash code equals and copy constructors. So that's pretty cool. Clojure has really amazing value support. All of its collections are strictly immutable, and it has all kinds of little functions and abilities to go in there and pick your collections apart and put them back together and analyze them. It also has something called a def record, which also effectively creates something like a case class. The key takeaway here, though, is that Java, even though you now have lambdas, still has no value support. Its collections are all mutable. Its classes are mutable. Now, if you've read Effective Java says you can make immutable classes. It requires writing a lot of code, even though you're still doomed when it comes to collections. So let's look at another example. Now we're actually going to write a little bit slightly less trivial programs. So car shopping, this is a trivial trade analysis example. If you do any sort of technical or scientific computing, you may at some point be asked to evaluate different options and figure out what's the best one. So this, even though it's a trivial example, illustrates many good, real complex problems. So here's our problem. We're going to create a sampling of items. In this case, they're cars. I'm going to evaluate each one and then return the best one. Pretty simple. Okay, so here's the Java solution. Here's my car class. I have 4 fields: make, year, color, top speed. I have all my standard Java getters and setters. And I also override 2 strings so that if I print it out, I don't get something that looks weird. Here's my test driver class. As we know, in object-oriented programming, methods belong to types. So what would evaluate a car? Well, a test driver would evaluate a car, so it has this rank function. I'm just going to make it static for simplicity, so I'm assuming all test drivers are the same. In this case, I have an extremely complicated evaluation function, which all I care about is color. And so red is better than everything else, and then there are other rankings for different colors. In real life, of course, you could have a very complicated function, not something as simple as this, but I just want to keep things simple for the sake of our example. Okay, so now here's where the function actually, or the code actually gets invoked. We have this car purchasing model. I want to create a bunch of cars by first having a list of color options. Then I want to make a collection of cars, so I build a car every time, and I vary the color. I'm iterating over the colors. And then the last thing I do is I have this map called rank. It's a map of cars to their scores. And I pass that in the test driver. So I get my score. After I do that, I then iterate over my results, and I have a best car that's null and a best score that's worse than any possible score. And I iterate over that, and if I get something better, I update it, and then finally I print that out. So there's our complete Java example. Okay, let's see what the Clojure solution looks like. Okay, this is the whole thing. I don't need to go through multiple slides to get to the answer. So I define my color options, red, green, white, black, beige. Now I could use strings like I did in the last example. I'm using something here called a keyword. It doesn't really matter. I define a basic car rather than using a class here. I would rather just use a data structure. That's the Clojure way. I now define all of my cars. This is where things may start looking a little unfamiliar. I map, talked about mapping before, over all of my color options, and into my basic car, I remap that color with the color from my color option. So after I make this call, I now have 5 different cars, one of each color. I then have a rank function. Define means define a function. And that is probably pretty readable too, even though it's a different language. It just ranks your car based on color. And then I do something called a rank map. I define a data structure called a rank map, and it uses this thing called a zip map. Zipping is something that you do in functional programming, in which you have 2 data structures and you line them up next to each other and you zip down them and you do something to that combination. And in zip map, the things on the left data structure become keys, the things on the right data structure become values, so you can quickly assemble a map out of data. So I'm zipping and creating a map for all cars. All my cars are my keys, and my rank, I'm mapping the rank function over all my cars, so the score is my value. Finally, I print the best car out by calling this thing called max key, and that says give me the maximum of a particular collection keying off of a certain function. So I'm keying off of the rank function. Apply just means apply that function to the collection. So here's what I get. The Java output prints out, I want a red Honda, and then the Clojure output prints out. I also want a red Honda. The formatting is just a little bit different. That's because in one I did toString. The other one, Clojure has nice, pretty printing of all of its data structure, so I just pasted that in. So let's compare what we get. In Java, I have 3 files, 3 classes, 110 lines of code. In Clojure, I had 1 file, 17 lines of code. I was able to fit the entire example on one slide. So some observations. How did I represent my data? Java used mutable classes. Care had to be taken to ensure consistency. Every time I stepped through and I made a new car, I had to make sure I filled in every field. If I were stepping through there and I didn't quite step to the right place, my state wouldn't quite be where I wanted as I looked at it. One thing that is important here is I am stuck with the implementation I designed. If I said, well, I really care about the interior of my car, how would I add that? Well, I have a rigid hierarchy. My car does not have a field for interior, so I'd have to go and change my API. So, it's not particularly flexible. Finally, the code is not concurrent. Nothing about it is immutable. The collections are not immutable. The classes are mutable. I really can't do anything in terms of parallelization. Clojure, on the other hand, use strictly immutable data structures. So I have guaranteed concurrency. I can add fields at will. So because I used a map, I could easily just throw in a field for the interior of the car or anything else that I want to. Parallelization also is trivial. So instead of calling map, I can call something called pmap for parallel map. That's something that's just part of the language. Scala has similar parallel constructs. One thing to keep in mind, though, if your overhead of the threading is greater than the overhead of the calculation, you probably don't want to call pmap because it's going to get worse. Because this is such a simple example, I would not actually want to do that here. But in a real-world case with really complex things I want to analyze, I might want to do that. Okay, so how did I use functions? In this Java, I really didn't use any functions. This really was a lot more about data representations than functions. Clojure, though, makes heavy use of functions. It's all about having little functions to disassemble my constructs and build new ones and analyze them. So some of the functions I use were map into, zipmap, apply, maxkey. If you want to learn more, go use Google. Okay, finally, let's talk about our ranking function, how I rank the car. The ranker function was tied to a test driver, and it's only good for a car that has 0 reuse. I could never use that for anything but test drivers and cars. However, if color was the only applicable field, I could create an iColor and an iColor evaluator, and I could have, but then I'd have to declare that interface everywhere that matters. The Clojure ranker, on the other hand, only looked at the relevant field within the map. It only looked at color. And so anything that has color, I could use this function for. By extension, any evaluation function that pulls out fields and looks at them, as long as those fields are present, I can use that function everywhere. For example, if I wanted to evaluate a refrigerator or a cat, I could do that. I want a red car, a red refrigerator, and a red cat. It all just works. Was it unfair to Java? It seemed like this was kind of a beatdown. I mean, everything seems to be better about the Clojure version than the Java version. Did I do anything to, to be mean to Java in this case, to bias it? Well, I don't really think so. I could do some things differently. I could make car immutable with equals hashcode copy and default constructors. That's what effective Java tells you to do. If you ever read effective Java, by the way, by the time you get to the end, what effective Java is really telling you to do is be functional. So, if I do this, I really have to write even more code to implement hashcode and equals and copy. And a lot of code just gets moved around. It really doesn't save me anything. In fact, it's more code, 126 lines of code. Either way, I mean, either solution is pretty standard Java. Just for grins, I've included in here so you can look at it offline. iColor, data. Here's an immutable car, which fortunately I have an IDE to generate all these ugly hash code and equals methods. You just get that for free with other languages. Test driver is pretty much the same. It takes an iColor instead of a car. The improved car purchasing model. There is one thing here to point out that's kind of nice. Because I have an immutable car, I can quickly assemble new cars by calling this default car set color. So it does an update on the car and makes a new one. So please don't make me do this again. It's a lot of code to illustrate a point. I hope I made the point. Okay, so in summary, I provided 2 solutions, object-oriented functional, to the same problem. The functional programming implementation was smaller, it was concurrent, it was more flexible, it was more reusable. I've been doing FP for probably 4 or 5 years now, mostly Scala. About the last 6 months to a year has been Clojure. These results are typical. Okay, my last example is Conway's Game of Life. This is kind of cool. One thing you may have pointed out on the last, or noticed on the last example, was that you could say, well, you kind of cheated because there isn't really any mutable state. There's no buttons and GUIs and things where I have to manage this big state machine like I would for a desktop application. So, you know, if I just have some top to bottom things, sure, some kind of a functional language is pretty easy there. What if I have a stateful application? So let's see if we can do that. So Conway's Game of Life, if you're not familiar with it, is a cellular automaton. In fact, I'm just going to switch over and show you the program. Here it is. So I have this grid of cells, and the green cells are alive and red cells are dead. I can step forward, and I have rules for how things evolve over time. If a live cell has 2 or 3 live neighbors, it stays alive. It has just the right population density. If a dead, otherwise it dies. If a dead cell has exactly 3 neighbors, then a new cell is reproduced, and so it becomes live. So those are the basic rules, and so you can step forward. And the cool thing about the Game of Life is that as it moves forward, you see these cool patterns emerge. So there are some data structures that are stable. For example, if you look up here in the top center, that one just got eaten. Top left, there's a little square of 4 pixels. See where my mouse is. They're alive, and they'll have exactly 3 elements next to them, so they're always going to stay alive until something bumps into them and eats them. And there are little blinkies where you'll have 3 in a row, and the top ones die, and then it shifts, and then it goes back. And so, it's kind of a fun little simulation. And I can reset my simulation at any time I want to start over and sit there and stare at it because it's kind of fun to look at. I can stop my simulation. I can step through it manually if I want to. So Conway's Game of Life. It's pretty cool. These are the rules. I already talked about those. So implementation. I implemented this, in case you're wondering. I'm not going to provide a Java implementation that would be just too much. So instead, I provided a closure implementation. Here are my rules. Everything in here is strictly functional. That's one thing, really the important thing I want to point out here. Everything here is definitions. There's no mutable state. The only thing that really is not technically functional is GenCell. It calls math random. Random is not a function because you call random and you get different results. So it's not actually a function, but that's okay because we know it's what we want. My user interface, I use Java Swing. Really, the only important thing I want you to remember is down here, right above where I declare my JFrame, I have this ref. A ref is a reference. That is a closure concurrency primitive that allows me to bridge my functional and non-functional code. Okay, so a little information about the program. 2 files, 105 lines of code. The logic was 1 file, only 28 lines of code, and that's really where the meat is. The application logic, the JFrame, was 77 lines of code. So some observations. Program design. All the model logic was contained in a single file that was purely functional, with the exception of that one random call. The UI contained all of the state, all the UI state, as well as that one variable that held my functional state. Just as an observation, I was really lazy. When you look at this code, this is not the best Swing app ever written, but anyways, that's lots of into it, an exercise to the reader to improve. The actual domain model is managed by one single reference, a closure concurrency primitive, that ref. The reference can be watched for updates, and you set it using transactions. So you may look at that and think, well, this is just like beans, firing events. Well, that's not at all the same. Here we have safe concurrency. If the transaction fails, if concurrent modification occurs, if anything like that happens, it fails and it retries it, just as if you were doing like a database operation. And this is a very typical design if you're doing functional programming with stateful applications. Performance, just to kind of show under the hood what was going on. If I had a 1,000 by 1,000 grid, it takes about 100 milliseconds to compute. The 100 by 100, which is what I showed here, takes less than a millisecond to compute. The slowest part of this was the graphics performance. I didn't really spend much time doing double buffering and back buffering, so we could do that. We could speed it up if we wanted to. So in summary, you can have complex stateful applications written in functional style. The very common pattern is your rules and your logic are completely functional. You use concurrency primitives and closure. The user or the UI only interacts with that concurrency primitive. The primitive can be watched for changes, and so it separates concerns. You can have 3 things on my graphical piece, my thing that kind of bridges that reference, and then my rules, which are all stateful or stateless. Okay, that's the end. So in conclusion, functional programming is built on the idea of applying functions to values. And a key takeaway here is it's not just functions. If it was, then Java 8 would be good enough. You need more than just functions to be functional. You need values. You do not want side effects. It's a different way of thinking, but if you do it, you're going to write a lot less code, and you're going to have to be synchronous. And if you face it, since around 2005, 2006, we have been in a multi-core world. Computers are not getting faster, but we're getting more and more cores. So you need to learn how to write synchronous code one way or the other. So hey, might as well do it functionally because you get it for free. Java 8 has some elements of functional programming, but it is far away from being truly functional. Newer language have better support. Scala has functions and values. It does not have built-in concurrency primitives. If you are interested in Scala, you could just look at Akai, which does have concurrency primitives. My personal opinion, that's a little heavyweight. Clojure does everything. So if you're interested, check out Scala or Clojure, especially Clojure. Kind of my final shot is in terms of the learning curve. That's something people ask about a lot. One reason a lot of people like Scala is kind of a bridge language. It is both object-oriented and functional. So it's kind of nice. You can get up and running in just a couple of days writing Java-esque style code in Clojure. And then over a year or two, maybe you'll learn all the functional principles. That's what I did. And what I learned after I did all that is I thought, man, I really wish I had just done Clojure from the get-go. Either way, either one of them is going to be a win over just sticking with Java. So that's it. Do we have any questions? Yes.
Talking about Clojure, we've talked about this before.
Uh-huh.
When we talk about Clojure, they talk about this concept, the data.
Clojure data, homoiconicity.
Did I get it backwards?
Yeah, I didn't talk about that because that was part of that first 30 minutes that got whacked.
Okay. Okay.
But anyway, I will mention that. In functional languages, you really have a couple of types. You have functional languages that have the constructs I just talked about, and then you have the really powerful ones, which are the Lisps, and they have something called homoiconicity, which means that your code is data, meaning the code that you write is represented in the data structures of that language, which means that you can then write macros, which means you can, in runtime or compile time, you can manipulate the language and you can add new, you can actually essentially generate code. And anyways, there's all kinds of amazing things you can do with macros. It's a code generation, code modification facility. It makes the language extensible.
Was that reflected in those code snippets that you showed?
I didn't use any macros. Well, I did not write any macros. I did use macros. After a while, you kind of recognize what's a macro and what's a function if you're actually using Clojure, like if is a macro. Actually, I got to think about it. If might not be a macro, it might be a special form. But again, these are details. The thing that's important about a macro is in a function, everything evaluates left to right in Lisp. If there are things that get skipped or don't get evaluated, then you're probably either in a macro or a special form. But again, I'm speaking Sanskrit now, so.
One more?
Absolutely.
So, in my efforts to learn Clojure, and I'm asking you some of your recommendations. So there's a book called, that I tried going over, Joy of Clojure.
Joy of Clojure.
But I have to be honest, it didn't bring me a lot of joy.
Joy of Clojure can get a little deep. If you really are interested in Clojure, what I would do, there's a website called Clojure for the Brave and True. Go there and follow the examples there. He explains things in a very detailed, simplified manner. Kind of skips a lot of the more esoteric things for later. Like macros, I really don't, most people don't write a lot of macros. That's something, you can kind of avoid. I mean, really, there are a lot of basic constructs you can jump right into. And Clojure for the Brave and True is a good one.
But you still highly recommend that Joy of Clojure thing?
Joy of Clojure is an excellent book. But what I did is I started with the Joy of Clojure, read through it, and it's like, okay, I kind of get it, but then I went and did other things, Clojure for the Brave and True. Then I went back to Joy of Clojure. Once you've actually done a little bit of programming in Clojure, then you go to Joy of Clojure and you kind of get your feet wet, it makes a lot more sense.
Nice talk. I just want to do a comment. Just so this is functional programming is not some weird thing happening. CMU a couple of years ago implemented their computer vision library for object recognition in Haskell, functional programming completely.
Yeah, one thing that is an important point to kind of piggyback along that is that both Scala and Clojure have very much made an attempt, very successfully, I believe, to take functional programming out of the academic world. A lot of times people think that, well, Lisp is only for academics. And if you look at a lot of the big companies out there, Amazon, Puppet, Twitter, Netflix, they're all heavily using these functional languages. I would say right now predominantly it's more Scala, but you are also seeing a lot of Clojure examples as well. Any other questions? All right, well, thanks for your time. Hopefully you'll go and become a functional programmer now.